Okay, so the previous lecture was about pointers, and today we will continue this topic. The last slide was about different ways how we can pass arguments. I mentioned about these ways before talking about functions. But for us, the most important thing now is how we can improve the function performance. So how we can decrease the execution time. So I told you that if we pass arguments by value, so every argument is copied. So inside function we have a new variables with separate memory allocated. So in this case, the arguments, so original variables and the arguments inside function are not connected together. So whatever you do inside function, it doesn't affect the original values. The opposite was passing arguments by reference. So in this case, the argument in function is only a reference to the argument which was used in function call. So in this case, a and x are the same. So they share the same memory. So whatever you do inside the function, it will affect the variables which are arguments. Okay. So similar, but not the same, is passing variables by argument. So by pointer. So in this case, we pass not a value of argument, so not value of x, but we pass address. And inside function, we can get access to, by the reference, to value which is stored under this address, and we can affect it. So what are the benefit? We consider that the fastest way is passing arguments by reference, because in this case, the arguments are not copied. In case of pointers, addresses are copied. So here, two addresses has to be copied. So two new variables, pointers, are created, and the value of address x and y are copied to particular arguments. But if the variable or the value is bigger than, let's say, 4 or 8 bytes, the execution time is still the same, because we copy only pointers, not values. In case of function, when we pass arguments by value, the amount of memory which should be allocated and the execution time is dependent on the size of particular argument. So you have to, so compiler has to copy values of every argument by byte by byte. Yeah. So in general, this way is the slowest one. But you can see that this solutions has some drawbacks, because from inside of the function, I can modify the external arguments. Sometimes it's very useful. I showed you an example with getStatistics function. So we can use reference for passing arguments outside. So we can return more than a single value outside. But if we want to achieve higher performance, and at the same time we want to guarantee that the arguments are protected, okay, this solution seems to be a little bit risky. Okay, Mr. Korzeniowski, yeah, there. Not using a reference is slower, but safer. Yes, but there are solutions that we can use a reference, but we can achieve the same argument protection. So now I'd like to tell you something about this. So in C, so in C++, we can declare argument as const reference. So the const means that the argument is read only. So we can only we can't write it. So we can read its value, but we can't modify it. So in this case, the argument is passing by reference, so it's faster than passing by value, but it is protected against writing, so I can't modify it. Okay, if I want to do it, I can do it, but let's assume that it is impossible. So the best way how we can declare arguments is to pass them by reference. So this is the faster and or fastest and also the safe way of passing arguments. In fact, when we have arguments which are integers or floats or chars, we usually pass arguments by value, yeah. But for larger data types, for structures, classes, we will be talking about this. So passing argument by reference is, it is, let's say, state of the art that you should do it, okay? Because you save a lot of memory on a stack, because every variable is allocated on the stack. When you pass arguments by reference, the variable is not allocated because it is attached to existing external variable. So, so this is the most commonly used way of arguments, or defining arguments. The other possibility, if we pass arguments by pointer, so usually when we pass arguments, for example, arrays, we can declare it as a const integer. So in this case, we can read values under the pointer, or we can read values from array, but we can't write it. Okay? So maybe a single example. So let's assume that I have the function question. And here I'd like to pass argument, so array of characters. Okay, of course, we can add here, for example, conditional statements or something like that, but let's say that this is enough. And look, if I create question, are you sure? So look, here we have the warning that ISO C++11 doesn't allow for conversion from string literal to char. So here we have string literal. So this literal is treated as a constant. So I can't pass such literal to the function which was defined like this, because it should be, the argument should guarantee that this literal will not be changed. So in this case, I should use const. Similar. Okay, return a plus b. And now sum. Okay, so I pass two literals here, and now I'd like to convert them to reference. And look, the error tells me that there are no matching function for call sum because these elements are literals. So when I pass argument by reference, I can modify it from outside. So a equal 5. So when I pass 1, okay, it is impossible to modify it. So in this case, I should also declare this reference as constant. Of course, if I have int d equals 6, I can write here d, for example. So everything is okay. D is passed by reference. So I can modify it from inside the function. But if I pass arguments by reference because I'd like to achieve higher performance, I always should use const. So in this case, I can pass here the argument d. Okay, there is a message that, okay, it's const, so I shouldn't modify it. So I can pass here any variable, or I can pass here, for example, a literal as well. So so this is the proper way of argument passing when we want to achieve higher performance, and we want to pass both the literals and the standard variables. Remember that if you create or pass arguments by value, you can also pass literals and standard variables. So, but in case of reference, you should remember to use const. Now I'd like to tell you something about memory allocation. So far, I showed you how we can extract address of particular static variable or automatic variable. Now, I'd like to tell you how we can allocate memory dynamically. So I mean in runtime. So look, if we declare variables like this, it means that the variables are automatic variables. So the memory is allocated when program starts. So it is let's say pre-allocated. So the compiler knows what is the size of the memory or where particular variable is located. What else? Let's try to think that I have array of 100 elements, but because of some requirements, I need, okay, not 100, but 101. And what should be done? In this case, I should modify my code and recompile my program. So this is the only way how we can change the amount of memory when we declare array like this. So these variables are allocated automatically, and when we leave variable scope, so here is scope begin and here is scope end, when we leave this scope, these variables will be automatically deallocated, so they will be destroyed. So now I'd like to tell you how dynamic allocation works. So there are two ways, depending on the using C++ or C. For us, the C++ is the base programming language, so I only mention about allocation in C. So let's assume that we have pointer, and then when I'd like to allocate memory for a single variable, I call new operator. So I call new float, for example. It means allocate memory for a single float variable. So in this case, 4 bytes are allocated, and address of this area is returned. So now in PTR variable, the address of allocated memories is located. So if I have a pointer, I can modify value under this address. So new and type. So this is general rule how we can allocate memory for any type. If we want to allocate memory in C, not C++, there is a function called malloc, so memory alloc, and inside as an argument we have to define size of given type in bytes. So in this case, I can allocate memory for a single byte or for more bytes. Okay, but okay, don't worry. On your laboratory classes and during our course, we will use only new operator. Sometimes in one example or two examples, you will see a malloc. So I'd like to tell you only that it exists and how it works. In case of new, the new infers the size or the number of bytes to allocate from type. But look, what will happen if so here I allocated memory for PTR, and here 60 was inserted. Of course, the bytes were initialized with proper values based on IEEE standard. Yeah. So now I call a new float again. So what happened? What will happen if I perform this command again? What do you think? No? Are there any ideas? Okay, so look, if I use new float, okay, so look, if I use pointer new float, 4 bytes. So here is my mistake. So 4 bytes are allocated. So using the reference PTR, the proper value is wrote here. Okay. Now I perform this operation again. So I call new float. So what will happen if I call a new float again and I assign its value to PTR variable? No. Okay, this operation is legal, so you can use it. So in this case, somewhere in memory, again, 4 bytes will be allocated. And now the value in PTR will point not to 1002, but it will point, for example, to 1008. There are no guarantee that the value will or the next variable will be located, just after the previous variable. Okay, it can be located in any, let's say, in general, in any place in memory. So what happened now if I write the reference PTR is equal to 5. So here 5 will be written. But how to get access to the memory which was previously allocated? So are you able to get access to this area again? Yeah, we can't. Because the pointer was the only place where we stored information about the address of this area. So look, this area is still allocated, so it exists, and the compiler treats this value as or this place as reserved. The value 6.0 is still stored there, but I can't read it. So there are no way to refer to this area now. So it's, you know, similar to situation where when you take some notes or address or telephone number and you lost your, I don't know, email or sheet of paper you used for this purpose. Yeah. So this effect is commonly, it occurs commonly in programming. So sometimes probably you know the programs which takes more and more memory when they run. Yeah. So every, let's say every 2 days, I have to restart this program because it takes so the memory starts to be bigger than the available memory in my computer. So this is usually due to the fact that it allocates memory, but it doesn't release it. But the problem is that if I lost the address of memory which was allocated, I can't release it because, okay, I don't know what should be released. So this effect is called a memory leakage. And we should, when we allocate memory dynamically, we should prevent it. So the proper way how we can use or allocate memory is that before we override our pointer, we should release the memory. So how to release it? It's enough to use delete operator. So here I should use delete PTR. So it tells the OS to release this memory. So this memory will be marked as unallocated space. And now I can allocate a new piece of memory and assign it to my pointer. Of course, when you stop your application, the memory which was allocated, even it was orphaned, will be released, but only at the end. So it's because the memory context is allocated for every application, you know, independently. So if you close application, the whole memory context is wiped out. So, but if we want to create application which is able to work for a long period of time, you should remember to release memory or to use automatic variables. So in this case, they are released automatically. Okay. Of course, yeah, maybe the memory will be, the process will be killed by OS, but there are for Windows, I don't know how it works for Windows 10, but in Windows 7 and before, even this OS had also a memory leakage problems. for in general, for very complex application, it's not so easy to manage memory and to deallocate given the resource in a adequate time. So it exists. It exists also, for example, for Google Chrome and for other applications. Yeah. So look, allocating memory for a single variable, yeah, let's say it makes no sense. But it makes sense for allocating memory, for example, for arrays. So here you have an example. So I have pointer to float. So it can represent both a single variable as well as an array of floats. Now I ask the user how many elements he or she wants to insert, and when the number of elements is specified, I can allocate memory for as many elements as I need. So the decision is taken on the runtime. So in compiling time, I don't need to know how many elements will be here. It can be 3 as well as 1000. Unless dynamic allocation, I should write, let's say, float tab. Okay, assuming that the user will never insert more than 10,000 elements. But okay, if she or he wants to insert 10,001 element, okay, it doesn't work. So now I allocate memory in the size which is adequate for the user request. So allocating memory on this wave, so from this time, I get the array, so n elements array, and now I can use this variable the same like standard array. So there are no difference. But the difference is what will happen if, for example, here I have the start of the scope and here I have the end of the scope. So what happened with this variable if I leave the scope? So in this case, the automatic variable will be deallocated, but the dynamically allocated memory will be still allocated. So let's say that I have of course, here it makes no sense because the size is, not known in compiling time. But here I'd like to tell you about the difference. So now look, this array is allocated in this place. And if I leave this scope, it is still allocated, so it isn't released. But the question is, am I able to, get access to this array? So for example, array index 1 is equal. So look, am I able to write something like this? So look, the memory, the address of memory is remembered or stored in the pointer array. So if I leave the scope, this pointer is deallocated. So again, the memory leakage occurs. So in this case, I can't get access to memory, but the memory is still there. So it is orphaned. So to avoid the memory leakage, I should use delete array. Remember that if you want to release memory for array, using the delete array affects only a first byte, or not first byte, first element. So it releases only a single element from the array. So the 99 elements are still allocated, but using delete array, it will release the whole array here. Now I'd like to tell you something about, okay, I told you that we can allocate any size of array, but in fact it is not true, because you know that the memory is limited. So for example, for standard application, the memory which is available for this application without any changes in compiler settings, it is about 1 gigabyte. Of course, in memory we have not only the space for dynamically allocated variables, but we have also many other things. So in fact, the size of memory is less than 1 gigabyte. Okay, for most applications, this is enough. But what happened if I request more memory that it is available for me? So there are two ways. If we use malloc, the malloc returns the address of memory which was allocated. If it was failed, so the memory was not, or the size was, available size was smaller, it returns null value or null pointer. So in this case, I can check or verify whether it was succeeded or not. Remember that having enough memory doesn't guarantee that the memory will be allocated, because in dynamic allocation process, if I allocate memory for array, I expect that it should be continuous block of memory to allocate. But sometimes the memory for dynamically allocated variables can be fragmented. So look, let's say that I allocate memory for a single float, then I allocate for another item and for another one. And in this case, when I release, for example, memory for this element, here I have a gap. Okay, so even the memory, available memory is higher. Here I can only allocate the block which can be fitted in this space. So, malloc and new operator require the continuous block of memory to allocate. Here you have an example how we can write function which is called create tab, or so it aims to allocate the n elements array, and before memory or address will be returned, it checks for the whether the process was succeeded. If not, it terminates the program. In case of new operator, it works different. So let's say n. Okay. So now I'd like to allocate memory for n elements. I run it in debug mode. And now I should write the number of elements. Okay, so okay, so 1000 elements, allocation succeeded. And now if I run, maybe not. So let's say that I'd like to allocate, okay, so still it was succeeded. Okay, something is wrong. Okay, I tell you because maybe the compiler will optimize this code. Okay, because it analyzing this code, it see that I only try to get access to the first element. Let's try to do it for n-1. Maybe I increase. Okay. Still succeeded. Okay, I tell you what will happen if it failed. Okay, so in this case, for a new operator, if the memory was not allocated, the exception is thrown. So exception is a mechanism for C++ which can inform that something was wrong. I think now it's too early to tell you something about exceptions handling, but in fact, the exception stops my program. So it breaks my program. So other parts of the program are not processed. And I can handle exceptions. So I create something which is called a sandbox. Try. So try tells compiler, okay, try. This is sandbox, like for bump. Yeah. If something will happen, I can catch. So, and if the exception is thrown in this place, the further parts of this code are kept until catch. So in catch, I can, for example, see out allocation failed. And I can react for this event. If not, if there are no try catch, the program will be terminated. So this is the way how we can cope with or check whether memory was allocated or not in C, when we use new operator. Now I'd like to tell you about two-dimensional arrays. In fact, in C and C++, we have not only a single dimensional array like tab and the number of elements, but we can create the arrays of higher dimension. For example, tab 2 by 4 elements. So it creates a matrix 2 by 4 values. And to get access to particular element, I can use a double index operators. So in this case, I get access to the first element in the first row. So to fill elements with zeros, so fill the matrix with zeros, I have to use a nested loop, which traverse through rows and through columns, and I can get access to all elements. But in case of two-dimensional, Mr. Janiszewski, I don't understand your question. Here I have 2 by 4 elements. So the first index of the first element is 0. The second element is 1. No? So I have 2 elements. But indices changes from 0 to 1. For 4 elements, they changes from 0 to 3. So I don't understand why is 3 by 5. Okay, yeah. So look, if we want to allocate memory for two-dimensional array, let's say that I'd like to represent matrix or vectors. So look, when I allocate int tab 100 by 100 elements, I can store here an array of 100 by 100, or I can store here a vector which consists on 100 elements. a smaller matrix. But look, if I use it for representing matrix 3 by 3 elements, here I have 10,000 elements. Yeah, so the memory are able to store 1,000 elements. If I want to use it only for 3 by 3, I need only 9 elements from this matrix. So in case of two-dimensional array, using automatic allocation of the memory, okay, makes no sense. We lost a lot of memory here. And if even you have, let's say, 10,000 elements, but you want to store, for example, vector, which contains 101 elements by 1, this array is not enough. So now I'd like to tell you how we can allocate memory for two-dimensional array. So let's start to imagine that the memory is only one-dimensional array. So talking about pointers, I told you that every byte has a unique address. But bytes are located one after another. So if I'd like to create a two-dimensional array, in fact, I have to organize it as a set of one-dimensional array. So let's say that I have the first row, the second row, and the nth row. So every row is a one-dimensional array. But every row has a pointer, so has address. So now I create another array which stores addresses of every row. So here I have address of the first row, second row, the nth row. Okay. Okay, so in this array, elements are not integers like in rows, but they are pointer to integers because they store address of the first element in array. Okay, so now I'd like to represent, okay, here I have m elements, so every row consists of m elements, and here I have n addresses because I have n rows. So the question is, what is the type of the pointer which led me to store address to this array, to this one? So look, because the element is integer pointer, I need pointer to this element. So it will be int asterisk asterisk. Because int asterisk is a type of element, and int asterisk asterisk is pointer to this element. So look, the process of building two-dimensional array is performed in this code. So I have the address of the array of pointers, so the integer double pointer, and I allocate memory for array of type integer, a pointer to integer. Yeah? So in this process, this array is created. So here is the stage 1. Now, for every element in this array, so tab index I means, okay, address of the ith row, I allocate memory for a single row. So I allocate memory for the first, second, and so on row. So array of integers. Here I have array of pointers. Here I have array of integers. So look, performing these 2 steps, I get n rows and a single array which stores pointers. So if this process will be succeeded, I can use this array the same like standard 2-dimensional array. So I can get access to the first, so to the row and to the column using this code. So there are no, again, there are no difference in array handling, whether you use automatic array or dynamically allocated array. But there is difference because I have to release this area when I finished my okay, when I stop using this array. So in this case, look, the process of releasing or deallocating memory is opposite. So first, I deallocate memory for rows. So I call delete tab I. So for every address, I deallocate memory for particular row. And then I call delete tab. So it means delete the array of pointers. If you do it, opposite, so if you write delete tab, of course, it executes release of this array. But in this case, all rows will be orphaned. So they will be not accessible, but they still be allocated. Here is, quite important issue, but I will be talking about this issue later on. Now I'd like to only mention that we have, of course, pointers to variables to memory, but we can have also a pointers to function. So pointer to function is the, a pointer which can point for different functions of the same type and of the same arguments. But I will be talking about this later on. Okay, so now it's time to tell you something about the memory organization. So now I showed you how we can allocate memory dynamically. Talking about functions, I told you that there is something like stack. So when you call function on this stack, the function stores some elements like variables, like state of the parent function and so on. So for every function call, this stack grows. Okay, in fact, it grows down. Okay. When we allocate memory dynamically, these elements are stored in something which is called heap. And in case there is a difference between stack and heap. On stack, I can add elements here, but if the function is finished, the stack pointer returns up. So in this in fact, the allocation memory for automatic variable consists on, changing the information about where to stack finished. Yeah? And now, let's say that I have a recursive function call. So this is function, let's say, factorial 5. Here I have factorial 4, factorial 3, factorial 2, factorial 1, okay? And when factorial, I can deallocate memory for factorial 2 before I don't deallocate memory for factorial 1. So when factorial 1 is finished, this stack pointer points to this place. So I return up to the parent function. So now, if the parent function is finished, the stack pointer is moved here, yeah? And so on. So moving the top of the stack is the way how the memory is allocated and deallocated, yeah, on a stack. So there are no, way to stack fragmentation. The stack is a continuous area of memory. Now I have heap. So on heap, I allocate memory for variables dynamically. And in this case, I can allocate memory for particular variable and for other variable. So let's say that this variable was allocated as the first one. Okay, it's not, okay, sorry. So if I allocate memory for dynamically, I can deallocate memory in opposite or in any order. So there are no requirements like that, that the memory which was allocated first should be released last, okay? So when I allocate memory for variable, I can deallocate it in any time. So look, it creates a memory fragmentation. So when I request a new memory allocation, the memory manager tried to fit the requested memory in gaps which exist. But if all gaps are not enough, the heap size increased. So it increases. So you can see that after some time, when stack grows and heap grows, they can meet together. So in this case, the stack overflow or fragmentation fault or segmentation fault error is called. So it tells us that the memory, there are no memory for stack to allocate. Yeah, so remember that this effect may occur, and be careful. Okay. I told you how stack works, so how function, so what are the elements which are stored on a stack when we call function. But look, here you have the stack pointer. So when I call function, I allocate memory for arguments, remember returning value, the stack pointer is moved up. Then inside function, I can have a local variables, so the stack grows further. So when I return, so the function is terminated, or I leave the scope of the local function. So when I leave scope, the stack pointer is moved up. And then again, when I leave function, the stack pointer is moved up. So this is the way how memory is deallocated. There is a very important security issue here. That look, releasing memory here consists only on moving stack pointer. So the process knows where is the end of the stack. But these memory cells are still there. So the values which were here, they are not wiped out. No? So now I'd like to tell you something about the about this problem. Okay, here we have the YouTube video. I hope that you should be able to understood what is the problem here.
So on the 8th of April 2014, security advisory.
First, can you hear this guy properly? Yes, okay. So I'd like to tell you, or maybe not me, in this video, you can hear about something which was called a heartbleed vulnerability, which was found several years ago. It turns that that problem affected most of the servers which used OpenSSL protocol. OpenSSL protocol is commonly used protocol for communication with servers. So, and now this guy tries to explain what was the reason for that. I will stop in some places. I will stop and I will try to comment this video for you.
By people at Google and other places that have discovered a bug in a package called OpenSSL. One problem with a package like OpenSSL is that being so pervasive, if the bug does get into it, then it'll filter out onto lots and lots of machines. So to understand this heartbleed bug, we actually need to understand in detail how the heartbeat protocol works. Let's move into the office and actually understand how heartbeat works. Like all internet protocols, these are defined in the request for comments, or RFCs. And if you look down here, there'll be a link to where you can download this one, and you can go from there to find anyone. There's a heartbeat request, which we send out, and there's a heartbeat response, which comes back from the other side. They're made up of 3 or 4 things. We've got this.
So what is first? What is the heartbeat? Heartbeat is something like ping. So I can verify. So like I can verify using ping. I can verify whether particular computer is working on network. So using heartbeat, I can verify whether the OpenSSL service is alive. Yeah. So okay.
Type field, and this can either be a value of 1, which means request a heartbeat, or a value of 2, which means I'm sending a response to a request you've actually sent. We then have this payload, and this can be anything the person requesting the heartbeat likes. It's just some unique value. It doesn't even have to be unique, but it helps if it is, that they send to the server, and the server, when it responds, sends back exactly the same response there. Finally, we have what's called some padding, and this is at least 16 bytes of random data, which just bulks out the actual message that's sent. It's ignored by the other side, but it's there as part of the protocol. What this means, though, is that even though we know how big the message is, we don't know how big the payload is unless we actually send over the length of it, because we don't know how long the padding is either.
So look, the package which is sent to server contains something which is called payload. So payload is array of values, and these values are defined by the user, by the sender. But the user has to provide payload length, so the array length, and the values, so many values as the length is. Yeah. Okay.
So we also send over, before we send the payload, 2 bytes gives us the payload length. It means the payload can be anything up to 65,536 bytes in length. And that
So maximum size of payloads is 2. Because the length is 2 bytes, yeah. So maximum size of payload is 65 kilobytes.
That will get sent as part of the request, and the server's job is to copy that payload, create a response message around it, and send it back to me to tell me that it's met that response. And if we just look down here at the bottom, it says, if the payload length of a received heartbeat message is too large, the received heartbeat message must be discarded silently. What that means is, if I send you a message where the payload length doesn't make sense, for example, it's greater than the actual length of the message, then the server is meant to ignore that message completely, not try and process it and send a response, because it doesn't make sense. And it's that handling of that situation that causes the heartbleed bug in OpenSSL. OpenSSL is written in C, so we're going to look at the code here, but I'll walk you through it. So if you're not familiar with the C language, we should be able to follow it without any issues. So I've opened up a file here called t1lib, which is the file that contains implementation of the heartbeat extension. If we scroll right down to the bottom of the file, we find that there are a couple of functions that implement the heartbeat protocol. First one we're going to look at is this one called TLS1_heartbeat.
Jak świętować, to tylko z Pepsi. A jak coś poplątać, to świąteczne lampki.
I'm sorry for this product placement.
Grammarly does more than catch errors. With Grammarly, you can find really good...
Okay, sorry.
Actually responsible for sending the messages out over the connection. It does some checking to check there's no heartbeat already being sent. And then we come to this bit of code, which actually generates the message. And there's no problem with this code. It's generating the message in a way that makes sense. It's allocating memory here for the right length. It's putting in the relevant bytes. It's saying it's a request message. This is how big the payload is. It's 18 bytes long. It's generating the payload, and it's sending its random padding bytes out over. And then we can see here, called SSL3 write bytes, send that out over the network connection to the other side. So that's all fine. There doesn't seem to be any problems with that. But if we scroll up a bit, we come to the code which processes the heartbeat. That's in a function called TLS1 process heartbeat. And what this does, it gets sent a message that's been received from the other side, and it starts pressing that to see whether it's a valid heartbeat request. And if it is, it will generate the response to the other side. So it reads in from the package the heartbeat type, and it also extracts out the payload length from there. Now, one of the things you have to do when dealing with network protocols is that there is a defined method for how data is sent over the network. And that is what's called a big endian way of transmitting things. PC computers tend to be little endian and so on. So you sometimes have to convert between it. So that's why we have this function network to short here, which does that conversion for us. So we get the length of the payload. There's then some more code which does some tests. And then we say, if we've got a heartbeat request message, we're going to process that. And so it's going to generate the response. So the first thing it does is it allocates memory for the response message. So that's 1 byte for the type, in this case it's a heartbeat response, 2 bytes for the length of the payload, then however many bytes are required for the payload. And remember, it's read that from the actual packet that's come in. And it then creates this padding. In this case, it's going to generate 16 bytes again. So it allocates that memory, and assuming that gets allocated properly, it starts to fill in those details. So it's saying here that I want a response message, and so it says that's the type. And it sets the payload in there again. And again, it's having to convert it from the computer's type into the network type, so it's in the standardized format. So it's putting payload bytes in there. So that's the value it read in. And then it uses this function here, memcopy, which just copies a block of memory from one location to another to copy payload number of bytes from the original message which had the payload in it. It then adds the padding and sends the data out over the network. Well, what's the problem with that? That code works, and it works fine, providing the packets it is sent are standard. The problem comes, the heartbleed burgers it is comes, if the packet that we send isn't standard, it is crafted maliciously. And in particular, the key problem is this payload length that we use to copy the bytes from one memory location to another. We read that in from the packet that we send. And so if we create a packet that has a payload, say, of 64K, 65,536 bytes, but only actually provides, say, 8 bytes of data, when it starts to copy things, it's going to copy those 8 bytes of data, but this memcopy instruction here is going to carry on copying for another 65,528 worth of bytes. Now, where are those extra bytes going to come from? Well, they're going to come from whatever follows on in memory, in the computer's memory that's there. If we're lucky, that data will be meaningless. It'll be garbage that's been left in there, it doesn't make any sense. But it could also be details of previous requests, usernames, passwords, and if you're really unlucky, it could be the actual security certificates used to actually encrypt the data. Fixing this was really easy. They just added checks, like it described in the RFC, that the payload length made sense in the context of the length of the actual message.
Okay, I think that's enough. So look, what was the problem? That because if you deallocate variables, you only mark particular memory as deallocated, and you don't wipe out those variables. So if you allocate memory again, the value of your variable is, let's say, random, but it is not random in a sense that it is randomized, but it is random in the sense that okay, it is the remaining value, so the value of the previous process or previously allocated variable. So if the payload, let's say, was allocated somewhere here and only several bytes was sent in a request package, the further bytes are taken from the memory. So potentially I can read some sensitive informations. Okay, so what was the problem? The OpenSSL protocol existed for, let's say, more than 20 years before this problem was detected. What else? The heartbeat is the protocol which is commonly used, so I can use it, every 1 second or several, times per second. So I can dump from server the many bytes, and I can of course analyze it automatically to find some specific sections like keys, passwords, etc. Why this problem was discovered so late? Okay, I think that this problem was well known by certain groups of let's say hackers. So they were able to gather some sensitive information, but it was discovered by by a group which was focused on security issues very late. Yeah. Okay, so it shows you how because of the memory allocation, what is the problem with that? So my question is how we can protect against the information leaks in our application. So let's say that we have app, and in app we have, let's say, car password variable. Okay, probably this is the most popular password on the world. So if I leave the scope, this variable doesn't exist, but these values are still stored in memory. So what is the solution to to preserve, to access, or to read these values? Have you any ideas? Okay, the only way to protect is to wipe these variables out. So I can, for example, write a loop. So this is the only solution how we can protect against. Because if we release this variable, these values will be still there. So of course we shouldn't use it for every variable, but for very sensitive variables like certificates or passwords. It should be done. Okay, here we start a little different topic about structures. Then we connect it with pointers. But I think 2 minutes it's not enough to introduce this elements. So we finished for today. So thank you for your attention. Tomorrow we have 2 lectures about information engineering. So after the second lecture, there will be a short quiz. Yeah. Okay. So goodbye, and yeah, and we see you tomorrow.